I'm here to answer the rope problem. And the rope problem is when you have two spaceships and they're going the same speed. And now we have a rope between them. And these spaceships are quite large, so they're massive. And it's just a piece of rope, doesn't have a whole lot of strength. But the rope's between them, and they're moving through space at the same speed. Now they both speed up, and they go a quite appreciable fraction of the speed of light. And the question is, since the rope contracts, does it break? The answer is absolutely not. And I have a thought experiment which will prove it very well. Now for this experiment, I'm going to have, instead of just two spaceships, I'm going to have a spaceship too, so I can be the observer. And so that makes at least 3 spaceships. If you want, we'll have 4, and mine can have a trailer with a rope so they can see the same thing I'm seeing. Now, I'm going to make a black hole. And that's right here. Here's my spaceship, and it's got a rope. And here's my friend's spaceship, and it's got rope. So now, here, I'll put the black hole down here. Now, what we're going to do, we can't get too close to the black hole. So we're going to accelerate towards it, and we're going to go to here and loop around it and come back. We could do that in our thought experiment. And it's going to accelerate us to, I don't know, 98% of the speed of light. Well, that's our calculation. Of course, we won't notice because we're in the spaceship. But we will notice we won't notice the acceleration because it's gravitational. But nevertheless, an observer over here would certainly see our experiment and notice what we're doing. And here's that observer. I'll make him bigger. My marker is dying. So here we are, and we start towards, we're going to loop around here. Now when we loop around here, we're both going to do it at the same time in opposite directions, like that. So when we cross, we're going to see each other at a very high speed, about 99% of the speed of light. We're going to expect to see some contraction, and we will. Now, will the rope break? And I say, of course not. That's absurd. Because, look, we can look at each other now, and we realize we're the same size. And as we go down here, well, we're parallel. So, we keep verifying through our telescope they're the same size as us. And we know that because we were at rest here and we started the trip together. We simply diverged and got in position to go around there. So now we're going to go down here, and I'm going to draw the ship down here, the rope and the ship. It's going to loop around that black hole, and this one here is going to loop around that black hole. But now they're going very fast, but not according to themselves. According to themselves, everything else is going fast. They're just sitting there. So we have rulers too, and they know the distance. It's a 300-foot rope, so they can tell it when you're in the trailer and you're looking at the rope, or even if you're in the front spaceship, doesn't matter which spaceship you're in, you can look at that rope and it doesn't change. So now we're looking at each other, and me, I'm over here. I think this one's awful small. It's an illusion. Lorentz contraction is an illusion, but it's a very persistent illusion. It's an illusion that seems to include existence. Like massive objects that, yes, we can tell some things about them. We can verify these things, like in particle accelerators. We can see that there's actually time dilation. They make a particle last longer than it should because it's going faster. So it's a very persistent illusion, but the illusion is caused by the speed of light. And it's not always intuitive because of that damn Michelson-Morley failed experiment. And it was a very well done experiment. So the failure meant something, perhaps, and Lorentz figured that, made that little equation, and we're stuck with it. Here's the deal. The region of space that contains that rope, it's contracted to us, to the observer on the other spaceship, on the spaceship that's moving relative to it. That is, it looks contracted. We didn't contract it. We didn't do a damn thing to that other spaceship. All we did was fly by it fast. Now, can you make something break by flying by it fast? No. So, you can make it look like the whole region of space is smaller, but the thing is we don't see regions of space. We only see objects. So, we put the objects in the region of space and they look like they're closer together to us flying by. But they're not closer together. They're the same. It's an illusion. But as I say, it's a very persistent illusion, and I think the basic reason for it is that it's based on light, and light is energy, and mass and energy seem to be interchangeable somehow. Mass and energy seem to be the same thing, in a different form. And so, here is the big deal, the real incompatibility between quantum mechanics and relativity. Do we see fewer particles in the other spaceship? No, of course not. In quantum mechanics, everything's quantified. But relativity throws a wrench in it. For example, if I have an object going here, traveling like that, and I'm sitting here. So you see it's the angle at which it approaches is going to change. Now, you know, it's going to be a tangent right here, and it's moving slowly, and I'm measuring the distance to it, and it goes 1 Planck length per second. It's just moving slowly. And I can barely see it move because all I can see is a Planck length. I can't see anything smaller than that. So their hypothesis states. But then it's as I say, it's at a tangent at some point. I'm right here and it's moving this way. And now it's 1 Planck length further north. But how far is it away from me? It hasn't moved a whole Planck length because, you know, it's at a tangent. So, it's moved a small fraction of a Planck length. You show me a Planck length, I'll cut it in half because I have my mind's eye and I can grasp the infinite, and so can you. That causes a problem with quantifying things. You know, that's why as humans, we are always going to have a hard time conceptualizing what is real. We're just little animals running around, and we barely understand anything. Now, too bad we don't have intelligent life on Earth, but there's still time.